Imagine you've spent years building a software system in Java, C++, or Python. Now, a new technology comes along, a specialized library or a domain-specific language that can make your code much faster, easier to maintain, or capable of running efficiently on GPUs or other specialized hardware. Sounds great, right? There's just one problem. You now have to manually rewrite your existing code to use that new language or API. This process is slow, repetitive, and error-prone. A small mistake during the rewrite can change the behavior of the program, introducing bugs that are often difficult to detect. So naturally, we ask a simple question. Can AI automatically rewrite our code into a new language while guaranteeing that the new code behaves exactly the same as the original? Large language models have already shown impressive abilities in translating code from one language to another. But there's a catch. They can generate code that looks correct, but they cannot guarantee that the generated program is actually functionally equivalent to the original. Even if the code compiles successfully, subtle differences in behavior can still exist. On the other hand, the programming languages research community has developed techniques such as verified lifting, which use program synthesis and formal verification to mathematically prove that the translated program is correct. The downside? These techniques are usually designed for a single domain-specific language, require significant expert knowledge to build, and often involve complex symbolic search algorithms. So we have two worlds. One gives us flexibility, but no correctness guarantees. The other gives us correctness guarantees, but requires enormous engineering effort. What if we could combine the strengths of both? That's exactly what this paper, Verified Code Transpilation with LLMs, attempts to do. Instead of using a large language model only to generate code, the authors propose a system called LLM Lift that uses an LLM to generate both the translated program and a proof explaining why the translation is correct. These proofs are then checked using formal verification tools, ensuring that the generated code is mathematically equivalent to the original program. In other words, the LLM is responsible for creativity and reasoning, while the verifier is responsible for trust. This combination allows developers to automatically translate code into multiple domain-specific languages without sacrificing correctness. In this video, we'll understand why this problem is important, what verified lifting actually is, how the authors combine large language models with formal verification, and why this approach outperforms many previous symbolic techniques while requiring far less engineering effort. So let's get started. Before we understand what the authors have changed, we first need to understand how verified lifting works. Don't worry if the name sounds complicated. The idea is actually quite straightforward. Let's imagine we have an existing C++ program. Instead of translating it directly into a target language like NumPy or PyTorch, verified lifting performs the translation in three separate phases. These phases are search, verification, and code generation. Let's see what happens in each step. Suppose we have the C++ program shown in the paper. This program processes two images stored as two-dimensional arrays. It visits every pixel, adds the corresponding pixels from both images, subtracts 255, and stores the result in a new image. Now, instead of immediately generating NumPy code, verified lifting first tries to understand what the program is doing, rather than how it is doing it. Notice something interesting. The C++ code uses nested loops to process every pixel one by one. But libraries like NumPy don't work that way. They provide high-level operations that work on the entire matrix at once. So the goal is to recognize that these loops are simply performing two mathematical operations: matrix addition and scalar subtraction. The paper represents these operations using an intermediate representation, or IR. Think of the IR as a language that describes the meaning of operations without worrying about the exact syntax of NumPy or PyTorch. Instead of writing loops, the IR simply says, first perform matrix addition, then subtract 255 from every element. This compact description is called the program summary. For this example, the synthesized program summary is simply the following. This single expression captures exactly what dozens of lines of C++ code were doing. Now comes the most important step. How do we know this generated program summary is actually correct? This is where formal verification comes in. A theorem prover checks whether the original C++ program and the generated program summary produce exactly the same output for every possible input, not just the examples we tested, not just 1,000 test cases. Every valid input. This is much stronger than traditional testing. Now you might wonder, the original C++ program contains loops. How can a theorem prover reason about loops that may execute many times? For that, verified lifting also needs something called a loop invariant. A loop invariant is simply a logical statement that remains true before and after every iteration of the loop. You can think of it as a mathematical description of what the loop has accomplished so far. The verifier uses both the program summary and these loop invariants to prove that the generated program is functionally identical to the original source code. If the proof succeeds, we now have a mathematical guarantee that the translation is correct. Only after the verification succeeds do we move to the final step. The verified program summary is converted into actual executable NumPy code. Since the summary already describes high-level operations, this final translation is surprisingly simple. For our example, all those nested loops become just one line of NumPy code. That's the beauty of verified lifting. A long loop-based C++ implementation is transformed into a clean, high-level NumPy expression, while also guaranteeing that both programs behave exactly the same. Right. Now that we understand how traditional verified lifting works, let's look at the main contribution of this paper. The authors call their approach LLM lift. The goal is simple. Instead of relying on complicated symbolic search algorithms and handcrafted heuristics to find the correct program summary and loop invariants, why not use a large language model to generate them? But before building such a system, the authors first formalized the verified lifting problem. According to the paper, verified lifting depends on three main components. The first is the specification. The specification simply defines what correct means. For this paper, correctness means that the generated program and the original source program must produce exactly the same output for every possible input. The second component is the program space. Think of this as the search space. It defines all the possible combinations of DSL operators that the system is allowed to use. The third component is the certificate space. Remember, generating code is only half of the job. The verifier also needs mathematical evidence that the generated code is correct. That evidence usually comes in the form of loop invariants. The certificate space defines all the possible invariants that the system is allowed to consider during verification. So, the verified lifting problem becomes: find both a program summary and the required invariants such that the generated program is mathematically proven to be equivalent to the original program. Traditionally, solving this problem required sophisticated symbolic synthesis techniques like enumerative search, constraint solving, and deductive reasoning. These approaches work well, but they require years of research, DSL-specific engineering, and many manually designed heuristics. The authors wanted a much simpler solution. At this point, you might be wondering, why don't we simply ask large language models to convert C++ directly into NumPy? Unfortunately, that doesn't work reliably. The paper highlights two major problems. The first problem is correctness. Even if the generated code looks reasonable, there is no guarantee that it behaves exactly like the original program. Remember, verified lifting requires mathematical correctness, not just code that appears correct. The second problem is even more interesting. Many DSLs are new or domain-specific. Unlike Python or Java, these languages appear very little in the training data of large language models. As a result, LLMs often struggle to generate correct DSL code. Take a look at Figure 3. The authors asked GPT-4o to translate the C++ example into MLX, Apple's tensor processing framework. Instead of generating valid MLX code, the model hallucinated a completely non-existent library called ML-compute. This is a common issue when LLMs are asked to generate code in languages they have rarely seen during training. So, directly translating into the target DSL is not a reliable solution. To overcome these challenges, the authors introduced two very clever ideas. Instead of asking the LLM to generate NumPy, PyTorch, or MLX directly, They first ask it to generate Python code that represents the semantics of the DSL operators. Why Python? Because Python is one of the most common programming languages in the LLM's training data. The model understands Python extremely well. So instead of learning every new DSL, the LLM only needs to combine Python functions that describe the DSL operators. Later, these Python expressions can be automatically converted into the actual DSL syntax. This makes the approach much more general. Whenever a new DSL appears, we only need to define its operators in Python. The LLM can immediately start reasoning about it without any retraining. The second idea is equally important. The LLM is not the final decision maker. Instead, it acts as a candidate generator. It proposes a program summary and the required loop invariants. A formal verifier then checks whether these candidates are actually correct. If the verifier accepts them, we have a mathematically verified translation. If the verifier rejects them, the system simply asks the LLM to generate another candidate. This interaction between the LLM and the verifier follows a framework known as Oracle-guided inductive synthesis. You can think of it as a conversation. The LLM keeps proposing solutions. The verifier keeps checking them. The process continues until a correct solution is found. If we look back at Figure 2, this workflow becomes much easier to understand. First, the LLM generates a program summary. Then another LLM prompt generates the required loop invariants. A parser checks that both outputs only use the allowed DSL operators. The verifier then proves whether they are mathematically equivalent to the original program. If verification fails, a simple Boolean feedback signal is sent back, and the LLM tries again. Once verification succeeds, the verified program summary is finally converted into executable code for the target DSL. Another nice aspect of LLM Lift is that the authors do not fine-tune the language model. Instead, they rely on few-shot learning. This is important because new DSLs appear all the time. Collecting thousands of training examples and fine-tuning an LLM for every new DSL would be extremely expensive. Instead, they simply provide the LLM with a few examples inside the prompt. This allows the model to generalize to completely new DSLs without any additional training. The prompt itself is surprisingly simple. As shown in Figure 4, it contains three main parts. First, a task instruction, telling the model to rewrite the source code using only the given DSL operators. Second, the DSL operator definitions, written in Python. These definitions explain what each operator does. Finally, the source program itself, which acts as the specification that the generated program must match. With only these three ingredients, the LLM is able to reason about the source program and generate a high-level program summary. Now that we understand how LLM Lift works, the obvious question is, does it actually work better than existing verified lifting tools? To answer this, the authors evaluated LLM Lift on 4 completely different application domains. This is important because they aren't testing on just one compiler or one DSL. They want to see whether their approach can generalize across very different kinds of programming languages. Let's look at each experiment. The first domain is distributed computing. Here, the task is to convert ordinary sequential Java programs into Apache Spark programs. Spark is a popular framework used for processing massive datasets across clusters of computers. Instead of writing complicated distributed code yourself, Spark provides high-level operations like map and reduce that automatically distribute the computation. The challenge is to automatically recognize that a sequential algorithm can be expressed using these distributed operations. The authors compare LLM Lift with a previous verified lifting system called MetaLift, which relies on symbolic program synthesis. Both systems were evaluated on 45 benchmarks. The results are quite impressive. MetaLift successfully solved 40 out of 45 benchmarks. LLM Lift solved 44 out of 45. Not only did it solve 4 additional benchmarks, but it was also much faster. On average, LLM Lift completed each benchmark in less than 1 minute, whereas MetaLift required around 3 minutes. But perhaps the most interesting result isn't the speed. It's the engineering effort. MetaLift requires over 1,000 lines of code to manually describe the search space and heuristics. LLM-Lift replaces all of that with roughly 100 lines of prompt instructions. That's a huge reduction in development effort. The second experiment focuses on programmable network switches. Modern switches can execute custom packet processing algorithms. However, programming them is difficult because they use their own specialized instruction set. The goal here is to translate ordinary C programs into these low-level hardware instructions. Unlike the previous experiment, these programs don't contain loops. That means no loop invariants are needed. Again, the authors compare LLM-Lift with MetaLift. This time, both systems successfully solved all 10 benchmarks. However, LLM-Lift was roughly 3 times faster. Even more importantly, MetaLift again required over 1,000 lines of handcrafted search space descriptions, while LLM-Lift needed only around 70 lines of prompts. So once again, the authors achieved similar or better performance with dramatically less manual engineering. The third experiment is perhaps even more interesting. It focuses on Taco, a compiler designed for tensor computations. Tensor computations are everywhere in machine learning, scientific computing, and numerical simulations. The goal is to translate ordinary C++ programs into Taco's high-level tensor operations. The baseline here is a verified lifting tool called C2Taco. It uses an enumerative search algorithm. Out of 60 benchmarks, C2Taco successfully solved 57. LLM-Lift solved all 60. The 3 benchmarks that C2Taco failed on required searching through deeper and more complex expressions. Its symbolic search simply became too expensive. Even extending the timeout to an entire day wasn't enough. LLM-Lift, on the other hand, generated the correct solutions almost immediately. The difference in solving time is also striking. C2Taco required an average of 41 seconds. LLM-Lift solved the same problems in only about 2 seconds. And just like before, the amount of handwritten engineering dropped from over 1,000 lines of heuristics to roughly 100 lines of prompts. The final experiment evaluates LLM-Lift on another tensor processing framework called TensIR. This framework is designed to automatically translate sequential programs into efficient implementations that can run on CPUs, GPUs, and several other hardware backends. The authors compare LLM-Lift with the existing verified lifting system called Transpilation. Both systems successfully solved all 23 benchmarks. At first glance, this might look like a tie, but there's an important difference. Transpilation achieves this performance only because it relies on 3 carefully designed domain-specific optimizations. Implementing these optimizations required over 1,200 lines of expert-written code. LLM-Lift doesn't use any handcrafted heuristics at all. Instead, it relies on prompts and the reasoning ability of the language model. To highlight this difference, the authors disabled Transpilation's optimizations. Without those optimizations, Transpilation could solve only 5 out of 23 benchmarks. LLM-Lift still solved all 23. It was also slightly faster on average. The authors also wanted to answer another interesting question. Remember that LLM-Lift generates the program summary and the loop invariant in 2 separate steps. But is that really necessary? Why not ask the LLM to generate both of them together in a single prompt? At first, generating everything in one shot sounds like the simpler solution. So the authors decided to test it. For this experiment, they focused on the tensor processing domain, which is actually the most challenging one in their evaluation. The corresponding DSL contains 37 different operators, making it a good benchmark for testing the robustness of the approach. Instead of using 2 separate prompts, they merged both prompts into a single one. The LLM now had to generate both the program summary and the loop invariants simultaneously. Everything else remained the same, including the query budget. The results were quite revealing. Using the single-phase approach, LLM-Lift successfully solved 20 out of 23 benchmarks. In contrast, the original 2-phase approach solved all 23 benchmarks. So separating the problem into 2 smaller tasks actually led to better performance. The authors believe there are 2 main reasons. First, generating a program summary is already a challenging reasoning task. Generating correct loop invariants is even harder. Asking the model to solve both problems at the same time increases the overall complexity of the prompt. The model has more things to reason about simultaneously, making mistakes more likely. The second reason is even more interesting. In the two-phase approach, the model first generates the program summary. Then, when generating the loop invariant, it already has access to that program summary. In other words, the invariant is not generated from scratch. Instead, it is generated with knowledge of the solution that was found in the previous step. This gives the model additional context and makes it much easier to reason about what properties must remain true throughout the execution of the loop. So, what is the main takeaway from this paper? The authors present a new approach called LLM Lift, which combines the reasoning capabilities of large language models with the reliability of formal verification to perform verified code transpilation. Across 4 different application domains, the approach consistently achieved results that were comparable to or even better than existing verified lifting tools. It solved more benchmarks in several cases, reduced transpilation time, and perhaps most importantly, dramatically reduced the amount of manual engineering required to build verified transpilers. This work shows that LLMs don't have to replace traditional program synthesis and formal verification. Instead, they can work together. Of course, like any research work, LLM Lift also has some limitations. One limitation is that after generating a program summary, the system only performs syntactic filtering. In other words, it checks whether the generated expression follows the allowed DSL syntax before sending it to the verifier. The authors suggest that adding a semantic filtering step such as testing the generated program on a few input-output examples could eliminate incorrect candidates even earlier and make the overall process more efficient. Another limitation is the feedback mechanism. Currently, the verifier simply returns a Boolean answer. Either the generated program is correct or it isn't. The authors believe that richer feedback, such as counterexamples from the theorem prover or compiler error messages, could help guide the LLM toward correct solutions much more efficiently. These are promising directions for future research. Overall, I think this paper is an excellent example of how the strengths of AI and formal methods can be combined. That brings us to the end of this paper. If you'd like to dive deeper into the implementation details, proofs, prompts, and additional experiments that we couldn't cover in this video, I highly recommend reading the original research paper. I've included the link to the paper in the description below. If you found this video helpful, consider liking the video and subscribing to the channel for more research paper breakdowns.